Okay, let's continue our lecture. Here is kind of one theorem from Kytölä's lecture notes, lemma 2.19, called First Properties of Measures. This is actually, in a nutshell, lots of important fundamental things about measures. And let's study how this theorem is proved and how it works. So what do? We assume that the mu is some measure, any measure, nothing else. And then there are 5 properties that are claimed. So let's study them in detail, each of them. First of all, there's property A. So for any measure, the property says that there's finite additivity instead of countable sets. So we can also have finitely many, a disjoint union. Again, the word disjoint is important. For disjoint unions, the measure of the union is the sum of the measures. And how is this proved? So it's quite easy. So given A1 up to AN, so assume that we are given some measurable sets, A1 up to AN, disjoint. So then define AN plus 1 to be the empty set, AN plus 2 to be the empty set, and so on. So we define these to be empty. Then what happens is that we have an infinite sequence, and this infinite collection is still a disjoint collection because these empty sets are of course disjoint from everything by definition. And so now we can say that the measure of A1 union up to AN by adding these empty sets, so we are not doing much. We have a union of A1 union A2 up to infinity, and now we use this countable additivity property, which was the definition of a measure. So for the infinite disjoint collection, so we get the sum of these measures here. Sorry, now we have the sum index. We are using n to be fixed, so we need the different summing index. Let's call it k. And now, because the sets from n plus 1 onwards are empty sets, so then these measures are 0. So then we only have here the sum from k from 1 up to n mu a k. And actually this was what we wanted to prove. So that's the proof of part A. And now I want you to look, okay, we were counting with the infinite arithmetic. So we were including that, okay, possibly some of these things that we have in the sum could be infinities. Now you should check that, okay, nothing goes wrong there. Does somebody see something going wrong? Very good. Nobody sees anything wrong, so that's correct. There's nothing wrong. That was the proof of part A. Let's continue with proof of part B, and shout out if you want me to slow down. So I might not be seeing the chat window, but if you see that something is too fast, let me know. The second property is called monotonicity. So if A and B are measurable sets, then the claim is that, and if A is contained in B, so then we say that we claim that mu A is less than or equal to mu of B. What's the proof? Quite easy, basic and simple. So let's say, okay, let's think about what's the measure of B. We can represent the set as the union of A and then the set B minus A. And then these are disjoint. So now we can use the finite additivity. So part A was the finite additivity, so we know from part A now that this is the sum of mu A plus mu B set minus A. And now this thing could be 0 or infinite, but whatever it is, it's at least 0. So then it's at least mu of A. That's the end of the proof here. Any questions? I have a question. Are we sure that this B set minus A, so when we take this set difference, is that measurable? Is B, when we take A out, is it a measurable set? What do you think? Yes, it is, because this is equal to B intersection the A complement. And we know that A was measurable, then the complement of A is measurable as well. Then we have a intersection of two measurable sets that's measurable that we know already, so that's why it's measurable. And we are done with part B. Then we have part C. What about part C? What is it claiming? The claim is that the measure, the subadditivity. So it means that now instead of disjoint, we have any sets A1 up to AN. They are measurable, but they don't need to be disjoint. The claim is that there's a so-called union bound. So this is what is called the union bound in applied probability, in computer science, and so on. So the so-called union bound claims this. Why is this true? Well, there are maybe different ways of proving it. What would be the easiest thing? Let's say maybe this. Let's just look two sets, A1 and A2 first. And let's see, we can write this as the union A1, and then the union of, we only add points which are not already in A1. So we write this union in this form, okay? This union is the same as this union here. If you think, okay, I have A1 and then I have A2 here. So then let's see, this part is the A2 where we don't include A1. So if you look at this, the union of this, yeah, of course, it's the same thing. Right, and then now these are disjoint. So we can use finite additivity. That was part A. We get mu A1 plus mu A2, and then we take out A1. Then by part B, which was the monotonicity of the measure, so then the next thing, this is at most the measure of A2, because this is of course contained in A2, and A2 was this big set here. So that's it. We have done this proof for, in the case we have two elements. What about more than two? When n is bigger than 2, we can do induction. There was a discussion on Monday that, okay, can we do induction proofs for things? So this is one case where maybe induction is the easiest way to do. Are there questions about this part C? Very good, no questions. Or shout it out if you have, just shout out and open your mic if you have a question. Otherwise, I try to go a bit quicker these because, yeah, some things are quite elementary. What is part D? Well, this is less elementary. So let's say these A, B, C were rather trivial things to do, or let's say easy exercises or homeworks. Part D is a bit more demanding. It's called monotone convergence, and it's actually really important. So monotone convergence, what does it mean?
Can I ask something here?
Absolutely, absolutely.
I'll specify that the measurable set is just a subset of the sigma algebra, right?
Yes and no. You mean the right thing, but the right wording is that a measurable set is a member of the sigma algebra.
Yeah,
Because,
sure.
yes. So measurable set, when we say we have measurable sets, it means we have members of the sigma algebra. Precisely, thanks for the clarification. So now we assume that we have increasing sequence. Increasing means that A1 is contained in A2 and A3, A2 is contained in A3 and so on. So we are looking at increasing sets. And they are measurable, so it means that each of them is a member of the sigma algebra. And the claim is that then we denote A as the limit of this increasing sequence. So we denote A is the union J goes from 1 to infinity. And this is kind of what we could think it's the kind of increasing limit as in the terms of set theory. So we call it an increasing limit. You could think if you draw a picture, so you have A1 here. This is A1, then you have next set A2, which is a bit bigger, A3, A4, A5. So these sets are increasing all the time. We are adding more and more points. So you could actually ask, what's the limit? Is there a limit when you add more and more points, you continue forever? When you add more and more points, and if you look at this, what's the kind of this union? What does it mean? So if you continue and you think, does it end anywhere? So where does it end? Well, technically it ends in A because A has this infinity there. So this set A contains everything in any of the kind of sets where we are increasing. Yeah. And this is what is quite often denoted that we have increasing sets and then the union in the end as the limit. A very short notation is that we just write AN is increasing to A. So this is a very brief way of saying all of this here. And that's what we assume here. We assume that we have an increasing sequential limit with these sets. And then the claim is that then that the measures are also increasing in this sense. So now we are looking at the numbers. So that means this for numbers, xn increases to x means that x1 is less than or equal to x2, which is less than or equal to x3, and so on. And x is then the limit of xn when n goes to infinity. Is this limit well defined always? If this is a bounded sequence, then it's a well-defined real number, the limit. If this sequence is not bounded, then this limit is well defined in actually, again, in this extended number set. Okay. Now we know the claim of this result. That's a monotone convergence, kind of a monotone convergence theorem. You might know a monotone convergence theorem from measure theory. Actually, this is the essence of the monotone convergence theorem of the integral theory as well. This is really the essential part, and that's why I wanted to share the screen and that we do the proof and we look at the proof in detail, because it's not super hard. When all the definitions are nicely placed, this proof is actually quite easy. So let's see, how should we prove it? So I thought about it yesterday a bit, so maybe I thought yesterday that maybe there's a very, very brief way to prove it, but no, maybe there's not. So I tried to do, maybe I get a more clean proof than in Kalle Kytölä's lecture note, but no, after 5 minutes I gave up, and then this is actually the same proof as you can find in the lecture note. So we define B1 to be A1, we define B2 to be A2 set minus A1, and B3 A3 set minus A2. So let's see. A1 is here in the center. That's the core, kind of. Then B2 is now this set here. What is there? And then B3 is then this here, and so on. So we take kind of part by part, and we add kind of one slice and so on. So we can write this type of sequence of B1, B2, B3. And then what's the key thing here is that if you look at the union, if we take B1 union B2, union B3, etc. So what is this union? We take the core, we take then this annulus, then we take the second slice, and so on. We continue. So if you look at this union is equal to the same as the union of A1 union A2 up to infinity, and which is by definition this was the A. Yeah. Also, if we take this union from B1, B2, a finite union up to Bn, so this one is the same as A1 union A2 up to n. What's the difference? So the unions are the same, but why do we care about this B1, B2, B3? Again, the thing is that these are disjoint. So the original sets, these A1, A2, etc., these are not disjoint usually because they are contained in each other. So far from disjoint in general, but this B1, B2, B3, they are disjoint. And that's why if we take the measure of A1 union up to AN, we see that it's the same as the union measure of B1 union B2 up to Bn. And now because these are disjoint, so then we can say that it's the, maybe I used the sum notation, so it's the sum from 1 to n, the measure of Bk, okay, like this. And we also know that the measure of A, which is now the union up to infinity, so the measure of A is equal to mu of B1 union B2 up to infinity. Infinite, but infinite disjoint union. So it's an infinite disjoint union. And again, we know that there's the, by definition of a measure, there's the additivity. So this is an k from 1 to infinity of mu bk. All right. So if you look at this, what is mu of A? Okay, mu of A is here. We know it's the sum of this. It's the sum from k1 to infinity mu of bk. And think, okay, what is the sum from 1 to infinity actually? How do we define an infinite sum? So we actually know that we define an infinite sum. We look at this part. So this thing is actually the limit when n goes to infinity, k from 1 to n mu bk. This is how we define this infinite sum. We sum up to n, and then we sum one more, and we sum up to infinity. So that's the limit of these sums up to n. But now let's catch up. So this is the limit of these things, and then these things where we take the limit is actually this thing here, and which is this thing here. Then what is there to do? The thing is to know that this A1, A2, etc. This was an increasing sequence of sets. So that one here is actually mu of AN as well. And so mu of AN is equal to this, and it's equal to sum from K1 from to 1 to n of mu of BK. So this thing here is just mu of AN. And we have a limit, and that limit is equal to mu of A. So that was it, actually. So now we can put the famous Halmos square here. And we are done with the proof, at least. Or are we? When are we done with the proof? Whenever the one who is listening or reading the proof is convinced that things are true. So my question is now, are you convinced that this is correct? Give me yes if you are convinced that this claim was correct.
Sorry, I'm a bit confused with the notation that mu of AN is equal to the mu of the union A1 up to AN.
Yes, good question. Let's yeah, that was maybe unclear. So we assume that A1 was contained in A2, and then that was these were contained. So AN is here. So AN is actually containing all of these. So if we think what's the union of A1 union A2 up to AN, well, because AN contains everything from before, so the union is just AN.
Ah, yes, Great.
So yes, good question. So there was nothing to do with measures in this part. It was just that the sets were increasing. So then the AN is containing all of these previous. Okay, very good question. Are there other questions? Then I still have the same question. Do you feel convinced that this is correct? Give me green light if yes. Give me red light that if you see that there's something confusing or maybe something suspicious still. Okay, you are giving me green light. I'm very happy. I will trust that you are convinced, because if you are not, so then we have not done anything. We haven't proved it. Either we have a proof or we don't have a proof. But hopefully you are convinced. This was the hardest, or maybe, yeah, most difficult part. Okay, you saw that it was not a long thing to do, but anyway, there's a fair amount of creativity to come up with this proof. So finally, there's part E, the final part. What is this claiming? It's claiming that this is actually a union bound again. But it's the infinite version of it. So we had a finite union bound. This is the infinite union bound. And let's say how to prove this. So maybe I think that should follow quite nicely from the previous part. So let's see. We know that mu of A. Wait. Let's see. Yes, let's do it. Let's do the proof so that we use the same notation. So let's use A as the union from K from 1 to infinity, AK. And then let's write mu of A. From previous part, we know that this is the limit when n goes to infinity. Mu of the union A2 up to AN, like this. And because now these, think about this union here. Think about this as sequence Bn. So this Bn is now a collection of increasing sets. It's increasing up to the A. And this is by part D. That's why this is true. And then by part finite subadditivity, and that was, I think it was part C. We use finite subadditivity to each of these members, and we know that each of these members was at most a mu of A1 plus up to mu of AN. This was the finite union bound. And what is this limit here? Well, the limit here, by definition of an infinite sum, so it's the sum from K from 1 to infinity, mu of AK. And actually, that's the claim. So if you look what we wanted to prove, we wanted to prove that this thing, the measure of the union, is less than the sum of the measures. So then this here is now mu of A. What's on the left and what's on the right? What's on the right? What is this? It is that what we have on the right side. So we can always again put this square and conclude the proof. And now it is time for questions. Do you have a question about this part? Very good. No questions. So then we conclude that we have proved this lemma. So let's open it in the PDF. And let's look at the lecture notes where we are now. We'll do another screen share. Here. And we conclude that, yes, We conclude that we have now proved lemma 2.19, first properties of measures. And we proved finite additivity, monotonicity, finite subadditivity, monotone convergence, which is the kind of crucial and important thing. Well, everything is important, of course. And then we proved this countable subadditivity, so-called union bound in general form here. You can also read Kalle's LaTeX version of the proof if you like, it's there. And the union bound, because it's so useful, it's rewritten here and it's once more there, so as this formula as a separate theorem, but we already did it, so there's not more to prove there. Okay. Then, okay, there's some discussion about other properties of measures, which we know from basic probability. The probability of the complement is 1 minus the probability of the event, and so on. So kind of familiar things. These are nice homeworks if you want to play with measures a bit. Then there's a discussion about the monotone convergence still. You could also ask what happens to decreasing limits, and so a decreasing sequence is like A1 is here, but then it's bigger than A2, and then that's bigger than A3, and so on. So there's a kind of decreasing sets here. You could ask, does this work for decreasing sets as well? And that's part of the homework to look at this decreasing sequence thing. Okay. And actually, the monotone convergence is repeated once more here. So as a theorem 2.22, if we have increasing events, so measurable sets now, and then the probabilities converge. And actually for probability measures, the decreasing things also work. The limit goes well.